Good afternoon, everyone, and welcome to the June 18th edition of ICLR's Friday Forum. My name is Mark Elliott, and today I have the honor of introducing Dr. Slobodan Simonovic and his presentation titled Floodplain Mapping over Canada, Investigating Performance at the Inundation Level and Understand the Dynamics of Population Flood Exposure. As a means of introduction, I'm just going to quote directly from Dr. Simonovic's nomination for the Fellowship of the Royal Society of Canada. Slobodan P. Simonovic is universally acknowledged as one of the world's leading authorities on the application of systems analysis to water and environmental management. He advanced the understanding of water environmental systems by providing decision makers with tools to support their sustainable management. He provides unparalleled contributions to global and local management of water that have improved the lives and livelihoods of millions of people worldwide. His work has had a significant impact on our understanding of system linkages between human beings and the built and natural environments that lead to sustainable water resources management and resilience as a new development paradigm. Before I hand things off to Dr. Simonovic, there are a few notes to be aware of for today's session. You can submit your questions at any time during the presentation to the designated Q&A chat box on the Zoom interface. These will be answered in a dedicated question and answer session immediately following the presentation. If you're experiencing any technical issues during the presentation that you would like us to be aware of, please use the general chat feature. I would also like to take a moment to advertise next month's Friday Forum, which will be on the related topic of Edmonton's approach to flood management, and will be presented by Susan Ansell, Director of One Water Planning for EPCOR Services. And with that bit of housekeeping out of the way, I'll now hand things off to Dr. Simonovic. Take it away, Slobodan.
Thank you very much, Mark. As you will see, I did expand a little bit the topic I'll be talking about, excuse me, by adding to performance at inundation level and population exposure analysis, also the climate change impacts analysis. So the presentation will start with a brief introduction and then talk about floodplain mapping methodology, use of evaluation of different reanalysis products, which are essential inputs into this type of analysis, and then utilization of the hydrodynamic model CaMa-Flood that we use to perform the floodplain mapping across the country. Maps generated in this way are utilized to do the analysis of the population flood exposure together with the side analysis of the globally available population data and their utility in this type of analysis. And at the end, I'll be talking about the investigation of the changes in floodplain regimes for future climates, again, utilizing this floodplain maps generated through the methodology developed in this work. The work I am presenting has been funded through the Collaborative Research Development Grant by NSERC and Chaucer reinsurers, which are in the meantime or during the tenure of the grant being sold to another company. A number of people participated in the research that I'll be talking about. I was definitely the lead, and postdoctoral fellow Dr. Mohit Mohanty did considerable work on two aspects: on the development of the methodology and the testing of the methodology and its implementation to assess the impacts of climate change. Ms. Bogdana Sredojevic was undergraduate student or research assistant, and during the last year, she did some work on the population exposure that I'll be talking about. So the main issue of the Thomson's news was kind of providing interesting comments and I think justification for the work that I'm going to report. In this May news, the kind of budget information was discussed from the point of flooding, from the impact on flooding and commitment of the government to provide over the next 12 years over billions of dollars for disaster mitigation and adaptation, and within that also over $60 million to kind of continue the work and finish floodplain mapping for high-risk areas together with provinces and territories. So my hope is that the work being done here and presented today will have some potential impact or utility in this process and the government supported activities. So the project as originally proposed had a number of objectives. The first one was to kind of develop the methodology that can be applied across the Canada. That means looking over the large regions with the high and produce the high resolution flood inundation maps. In that process, a number of things need to be kind of required to be tested, analyzed, and kind of investigated. The first one was the fidelity of the reanalysis runoff values or products. Then in assessing the impact on the population, the kind of utility of the global population data sets, and in the analysis of the climate impacts, climate change impacts, basically used for the first time, as far as I am aware, of the coupled model intercomparison project, six global climate models. 17 of these models are put into an ensemble that was used to observe the changes in flood inundation extent, changes in flood hazards through the assessment of the water depth, and changes in flood frequency. So let's start with a kind of methodology development. What you see on the screen is exactly the kind of methodological approach followed in the study. Floodplain management over the large region is now much more much easier with the presence and availability of the global data sets. Among them are the information on topography, on the information of the various hydrometeorological variables, and they're coming from kind of different sources and being utilized in the procedures like one that's presented here to achieve particular goals. And the goal here was high resolution floodplain or flood inundation mapping. Reanalysis products are usually the main input. They're using kind of systematic approach to reconstruct the historical global atmospheric circulation patterns, produce global data sets for the use in research as well as monitoring. The data that are produced through the reanalysis experiments are derived through kind of combination of the data assimilation scheme and numerical modeling, which consider millions of in situ remotely sensed observations from ground, satellites, aircrafts, and so on. Reanalysis products provide various inputs. In our particular case, the interest was in runoff, which is the main input into hydroclimatic model that we use to derive the maps. Four reassessment products were considered. They are listed here, as you can see. The first one is the US product Climate Forecast System Reanalysis by NOAA, which provides information every 6 hours for the period from 1979 to 2010 with spatial resolution of 0.3 degrees. ERA is European product, interim from European Center for Medium Range Weather Forecasting. It is a product that provides the data with the 3-hour time step for the period between 79 and today, and the spatial resolution of 0.75 degrees. MERA, or Modern Era Retrospective Analysis for Research and Application, is a NASA product, again US, 1 hourly time step, the time frame 79 to today, and the resolution, as you can see, 2/3 of degree times 1/2 of degree. And the fourth one we used is it is again NOAA product, American Regional Reanalysis product, which offers 3-hour interval data from 79 to today with a 0.3 degree spatial resolution. These 4 products were utilized in order to provide the runoff information that goes into our procedure. And procedure was focusing on the utilization of the hydrodynamic model known as a CaMa-Flood model. Explosion of global flood models, including list flood, glow freeze, CaMa-Flood, and others, is helping considerably floodplain type of analysis on the larger scale. There are some differences between the models in their availability, support, also applicability. And in some of the previous studies done by my research group, we investigated various models and opted for the CaMa-Flood model that has been developed by Professor Yamazaki from the University of Tokyo, who actually participated partly in this work that we provide. CaMa-Flood is utilizing global information, topography, water maps, river widths, and so on, and utilizing all this information to arrive at the river channel flood depths, the velocity, and overland flood depth. That is being done on a grid, on the grid base. The grid resolution is dictated by the input, in this case, reanalysis data products, as well as the global maps utilized by CaMa-Flood. At the end, the information generated on the various grid sizes was downscaled to a very high resolution, 1.1 kilometer, to produce the finally flood inundation maps. The flood flow information is then processed statistically through the implementation of the generalized extreme value distribution to arrive at the water levels as well as the water depth of the various return periods. In this analysis, we consider 100 and 200-year return period flooding, and that information is then mapped as well as verified through the process of comparing the maps generating using this procedure with the benchmark flood inundation maps, which are provided across the country by various agencies, various governments, and we selected 6 different basins to perform this kind of analysis. We also did the double check by comparing the results generating through this procedure with the observed flood events. For the observed flood events, we utilized the MODIS product, which is a near kind of real-time global flood mapping project, which offers a few historic flood events and on the kind of global scale, and was a useful input for our analysis. The map on top is showing the data that that are basically observed locations and providing the runoff information, data being collected and distributed by the Environment Canada, Environment and Climate Change Canada. And the map at the bottom is showing the 6 different basins, the Lower Fraser River Basin, Bow and Elbow, the Calgary, Assiniboine River Basin, and Red River Basin, Manitoba, and Grand River Basin, Ontario, St. John's River. So these 6 different basins were the basins that we call the benchmark basins. They offer the benchmark floodplain maps that were used in comparing with the product generated by our work. The implementation process was relatively complex, first starting with downloading the runoff information for each of the reanalysis products. Then we did some kind of preliminary analysis that station locations for which Environment Canada provides the observations of the runoff. We did the comparison between the observed and the reanalysis runoff values through the kind of correlation analysis in order to see how this reanalysis data look like. Fitting of the GEV distribution was done to extract 100 and 200 year return period floods, and the gridded 100 and 200 year runoffs were plugged into the CaMa-Flood model to derive maximum flood depth in meters and inundation extents in square kilometers for the entire country. The maps were downscaled to 1 by 1 kilometer spatial resolution after that, and in the kind of graphical presentation, visualization basically of the results, considering the size of the country and the number of grids exceeding millions. We performed some discretization of the water depths into 5 classes based on a kind of degree of severity to humans and economic losses. And we did the extraction of the information for the 6 selected basins so that we can do the comparison of the maps using some traditional statistical performance measures. The classification of the depth was along these kind of 5 levels, as you can see here, between 0 and 0.2 meters, 0.2 to 6, 0.6 to 1.5, 1.5, 3.5, and greater. So this was a kind of low, medium, high, and very high water depth. And the traditional statistics, including the kind of hit rate, false alarms ratio, the critical success index, as well as the error bias, were utilized to assess the quality of the match between the product, our product, and observed values. In this slide, I'm showing the kind of preliminary analysis or the comparison of the runoff between the observed Environment Canada observed values and the different reanalysis product values. As you can see, the figures A, B, C, and D correspond to different 4 different reanalysis products. The shade of red is indication, the dark red is indication of the good agreement between the reanalysis data and the Environment Canada observations. And you can see that there is already some difference between different reanalysis products. For example, NAR and ERA are showing much higher number of the red or darker red points compared to the other 2. Slowly starting to kind of differentiate the impact that potentially different products may have. Here I'm already getting into results. What you see on this particular slide is now the presentation of the water inundation. You know, this is all presented in these maps in a kind of million data points, and obviously it's not easy to kind of show. So we extracted like these 2 points so that you can see, at least through the color scheme, what the water depths at these kind of regions look like, or the inundations look like. The interesting information comes from the pie charts that are entered into this figure. The pie charts are showing the number of cells, grid cells, which belong to a particular water depth. So by color, you can recognize the difference between different water depths. And very interesting, again, the 4 graphs, 4 different reanalysis products. Very interesting is that the NAR and ERA are showing better results, like the number of cells in the category of high and very high, like dark purple and cherry. If you add these numbers together, they are very close to each other. And the other 2 products a little bit different results. We did the kind of mapping for using the 100-year flood in this particular case, and then the 200-year flood. Again, showing the difference in the inundation level, and is in this kind of zoomed areas, orange and green, you can kind of see the areas being kind of inundated, and the depth, the level of water depth. Obviously, with the 200-year flooding, we have a larger inundations and the water depth. Again, NAR and ERA reanalysis products providing better results, a little bit more accurate results than the other two products. I'm going very fast through the kind of results. My wish is to kind of project or give you the oversight of the overall work, and the details can be assessed or obtained through the references that I'm going to provide at the end, or question period. We did the comparison with the benchmark data for 6 selected basins. I'm showing in these next 2 graphs the results for the Red River Basin and the Fraser. So to better understand the figure, the colors are, because the colors are overlapping each other and it's not so easy to see. For example, blue color is under the kind of green, which is showing simulated and benchmark kind of together, and red is showing only the benchmark. So if you are trying to kind of see the difference between the kind of simulated and benchmark information, or the existing floodplain maps being provided or used by the authorities in these basins, you can kind of see that different products are providing different results. The figure is combined 100 and 200 year. So the figure A is an R product for 100-year flood, and figure E is an R product for 200. Figure B is ERA product for 100, and figure F is the ERA product and the other 4. So again, if you look at these two, it is really clear that NAR product is starting to kind of dominate. Very good agreement for such a large basin like a Red River Basin is obtained, with some areas where the difference is present, but measured by the 4 statistical criteria we use, the agreement is extremely high. For the lower Fraser River Basin, you can again see now the impact of different products. 100-year A is 100-year NAR, E is 200-year NAR, B is 100-year ERA, F is ERA, and CFSR and MERA are the remaining 2. And again, as you can see, the NAR product is starting to really dominate. There are some differences in the lower area where obviously the simulation with the CaMa-Flood model was not able to pick up, I assume, the impacts of sea level rise, tide, and so on. The focus and the model, the hydrodynamic CaMa-Flood hydrodynamic model, is very powerful for the inland kind of fluvial type of flooding, and in the coastal areas is not obviously performing at the same level. But altogether, when you look at the basin, we have a very high agreement. So the conclusion after the kind of presentation and analysis of the results and comparison with the benchmark data for the 6 selected basins for 2 return periods and 4 reanalysis products, is relatively clear that NAR is demonstrating superior performance in both, and This is what we actually used in the next analysis to compare the NAR floodplains data with the historic floods. Historic floods are obtained through the MODIS product. We utilized 1997 flood in the Red River Basin, which was named the flood of the century, the 2006 flood in the Red River Basin, the 2013 Calgary flood, 2008 flood in St. John River Basin, and 2011 in Assiniboine River Basin. Two colors are represented in these figures: blue simulated by CaMa-Flood and satellite-derived or MODIS observations, satellite-derived information. And as you can see, the NAR was pretty well capturing the inundation or providing agreement with during these particular events. There are some differences in the Calgary flood from 2013. The differences are obviously related to the quality of the information that's on both kind of side. You know, the information on the runoff that was obtained through the reanalysis product and converted through the hydrodynamic model into flood inundation, and that, as well as the differences in the observations that MODIS was providing. So to conclude this first part, I think we successfully developed the methodology for high resolution flood inundation analysis, developed the methodology, tested the methodology, documented and produced the maps for a 100-year return and 200-year return period. We also concluded that the NAR reanalysis product shows superior performance and can be used in future kind of analysis. We did that through the kind of first comparison with the observed hydrometric, comparing the runoff information from the reanalysis products with the observed Environment Canada data, and then by comparing the floodplain maps using the 6 test basin, the benchmark maps provided to us, and also the different events obtained through MODIS database. Let me now move to the kind of second topic. All this work is based on the methodology and the results that I kind of covered. And in the second step, we wanted to look at the population exposure in Canada. And that was done again through the kind of double analysis of performing the impact or population exposure analysis using Statistics Canada data, census population data, as well as using the globally available population data sets, so that we can see how these globally available data sets can be of some value in this type of analysis. Stats Canada data is of pretty good quality and I think sufficient quality for us to perform the exposure analysis, but in many places and countries that type of information is not available, and kind of global data sets may be of some more value. So how we did this analysis? 2 sets of floodplain maps were kind of generated using the procedure that I described in the first part. We did develop the maps for the categories of flood depth, all flood depths from 0 up to the maximum. And also we generated only the maps with the high and very high flood depths to see, how this inundation is changing. We utilized all the available census data for the population. That set by Statistics Canada includes data from 2006 to 2019 for 293 census divisions. And global population data sets were not available in the same kind of time series form, but we selected 1 year that was available for all 4 global data sets as well as the Stats Canada. That was the 2015, and we performed in 2015 also mapping that was able to kind of illustrate the difference between different data sets. The ending product was the kind of overlap of the floodplain maps and the population data gave us the kind of maps of the population exposure, which can be used as a measure of the vulnerability. Here is the information, again, mostly kind of preliminary information that provides the comparison between the various data sets for the 2015. The aerial resolution is the so-called census division. I mentioned there are 293. The figure A represents the Stats Canada data, and the remaining 4 figures are the different products of global population products. Looking kind of these 5 figures at the same screen is not very kind of easy, but there are obviously differences between different products. So to try better to kind of show this information, we did a kind of comparison, or we found the difference in population between the Statistics Canada data and the 4 different products, and then mapped that using different color scheme for the difference. The pie charts are kind of 2 indications. The red is showing the percent of the census divisions with underestimated population, and the blue is the percent of the census divisions with overestimated population. And the color scheme on within the map of Canada is indicating, you know, the various level of the population density within these census divisions. So it is kind of interesting that most of the underestimation is located in Alberta, Saskatchewan, Ontario, while the overestimation of the population is mostly in Quebec and the eastern part. We performed 3 experiments within this population assessment. The first one was the assessment of the population exposure over Canada for 6 flood-prone areas, or 6 basins that I introduced earlier, using only 2015, so that we can compare different population data sets, or impacts of different population data sets. Then we focused only on the Canadian data, on the Canadian census data, and basically for these 6 flood basins, 100-year and 200-year flood return period events, we performed assessments of the exposure. And because we had the data from 2006 to 2019, we were able also to look at the dynamics of the flood exposure and vulnerability, only utilizing the Canadian, the Stats Canada data. The results are in the tabular form here. I think this is providing the summary. Each row represents different population data set. The columns are representing the exposed population in millions. We are talking here about only 1 year, 2015. And the first column is showing all flood depths, and the second only high and very high flood depths, basically over 1.5 meters depth. This information is also provided for the 6 different basins that we used as a benchmark information. And this is for the all flood depths, and this is all for the high and very high. So you can see the distribution of the population being exposed within each of the basins. We will come probably to the question later on in the discussion, the way how this information can be extracted from all the maps may provide us ability to look at the province, or to look at part of the province, or to look at the larger region, including multiple provinces, instead of just focusing on the particular basins and so on. For the similar analysis was done for the 100-year and 200-year flood events. Again, the population, total population exposed, and then by the basin, by each of the basin. And for all these products, you can see that obviously Stats Canada is giving the kind of more precise information compared to other population products. And what is visible here, that approximately up to 4 million people in Canada is in the is in the floodplains up to 200-year return period. We wanted to see a little bit more and deeper, or obtain a little bit deeper understanding of what is happening in Canada. So utilizing the 13 years of data that we have from Stats Canada between 2006 and 19, we mapped the exposure, and the exposure was calculated as the ratio of the people within the particular flood depth to the total population within that census division. And the range between 5 and 10, 15, and above 20, which corresponds to very low, low, medium, high, and very high, was then mapped in this figure. So now, if you look at a little bit, obviously the northern parts of Canada are showing lower exposure, lower population. And kind of, southern parts, including east and west, are showing much higher exposure. The interesting is the change that's occurring. The A is starting year 2006. This is 2019, and you can see how, for example, very low, exposure is slowly changing. The blue in the north is changing to green, becoming higher level of exposure. Similar, if you look at the more exposed areas in the south, we can observe, look at the west coast, where the low exposure is towards this period of observation that we had the data for, changing to kind of medium, and in many areas to high and very high exposure. So this was also possible to put in a graphical form to kind of see the dynamics of the population change in the population exposure change. The dark line is showing the total number of census division being affected. And as you can see, from 2006, this number was kind of slowly declining until 2013, the big Calgary flood, which was recognized as a change point. And if you kind of perform the kind of averaging process, the dashed black line is showing that basically overall there is a rising slope and increase in the public exposure. This information is in contrast to what the mortality data provides from the MDOT database. Obviously, much more detailed analysis will be required to kind of see how the exposure can be compared to the mortality information. So the concluding part from this kind of analysis was the global population datasets can be used. The two products, WorldPop and Landscan, provide the closest estimates to the census data, but everything was based on the analysis done for the 1 year, for 2015. Most of the high and very high exposed divisions, census divisions, are located in the southern and western parts of Canada, Ontario, Alberta, British Columbia. And if you look at the 100-year, 200-year flood, up to 4 million people are exposed to high flood vulnerability. Let me move to the last part. This is the addition to the topic and my abstract for the announcement. This work was completed in the process between the different Friday forums. So I decided to kind of give you the overall results of that. This is a very, very new and very fresh product. What we have done here is, I think for the first time, somebody was published the information utilizing the coupled modeling and comparison project 6 data. This particular project is still in progress. They are claiming up to 100 GCMs will be available when the project is completed. We have carefully reviewed all the available GCM data, or the climate modeling data, and selected 17 of them that provide the information for the periods of our interest and runoff form that's required by the CaMa-Flood. The CMIP6 is changing now the emission scenarios. RCPs are being replaced with SSPs. SSPs are shared socioeconomic pathways, and they are supposed to describe the kind of how global society, demographics, and economics might change over the next century. You know, the period or the time frame the GCM models are providing the predictions. So we opted for 2 of these scenarios. Medium range forcing pathway is SSP2, and SSP5 is a kind of higher, more severe range of future forcing pathway. As you can see in this flow diagram, the procedure was relatively similar, but with a different purpose, focusing on different kind of impacts. We utilized the GCMs from the 6th project. We created an ensemble of these 17 different models, created 3 data sets for the historical period, 1980 to 2019, and the near and far future, 2020 to 60 and to 60 to 2100. And for each of the future, we utilize these two emission scenarios, SSP2 and SSP 8.5, medium. And so that also we utilize the historical information to kind of compare with the Environment Canada observations and confirm how the new climate models are matching the historically observed data. Then this information, this kind of runoff information, is again processed through the CaMa-Flood model in the same way as I described earlier, generating the river channel flow depth, velocity, and extent, overland extent, then downscaled. And for these 3 periods, historical, near, and far future, we created the 100-year and 200-year return period maps that were then able to help us analyze the change in the frequency of the flood events, in the flood inundation extent, as well as the flood hazard in the form of the water dash. So the implementation step started with the runoff observation from GCMs in comparison with the Environment Canada data for the confirmation. Then flood inundation modeling, including the statistical analysis and extreme value analysis to extract the 100-year and 200-year return period floods, comparison of inundations over 6 flood-prone basins as selected earlier, using the 4 performance metrics as introduced earlier, and finally present the information in the form of the change in the inundation extent, flood hazard, through the change in the 5 classes of depth and quantification of the frequency, change in the frequency. These are the results of the preliminary kind of analysis of the runoff. So the four different statistics, correlation, bias, mean absolute, and root mean square error, were calculated between the Environment Canada data and the 70 ensemble of the 17 GCMs from the CNIP6. The first graph showing the kind of correlation requires focus on the darker red areas, the higher concentration. As you can see, pretty well agreement is obtained. Similar thing with the bias. Pretty good results are visible, and mean absolute error less than 25 cubic meters, and the root mean square error now less than 40 kind of indicate also pretty good agreement between the historical runs of these 17 climate models compared to observed information. The detailed statistics are available for those who would like to go into details. We kind of presented the results for all these 6 different basins for 100 and 200 year return period for the 4 statistics that were calculated. And then in looking how to present the results in a graphical form, we started with this so-called heat diagrams, which are showing for the major river basins over Canada, what is the percentage change in the left side of the screen in 100-year flood, and what is the percent change in a 200-year flood for the 2 emission scenarios in near and far future. So if you look at the kind of heat diagram, the central parts of Canada, Ontario, Quebec, Great Lakes area are showing, considerable increase in the or change for almost all the scenarios and all emission scenarios and all the future periods. For a 200-year flood, we are seeing, very similar picture. It is very clear that for the higher, for the more severe emission scenario, the change is, the red is darker or the change is higher than for the medium scenario. The kind of low change is observed in the kind of northern parts, as well as some areas in the west. Also, we mapped this information in these 2 maps that you will see are the kind of flood hazard represented through the water depth. Again, the water depth analyzed into these 5 different classifications. The indication, if you zoom into different areas, you will see the basically increased or higher water depths appearing across most of the country. Obviously, different regions have a different kind of change in that. The graphs are showing for kind of historical, near future, medium scenario, and more severe scenario, and far future, medium, and more. Obviously, the far future, the basically figures D and E are showing the most significant changes. Similar map is generated for 200-year return period. As you can see, more areas are, if you look at the focused selected areas, more areas are under dark blue and purple color, or the obvious indication of the increase in the flood hazard in the future as a consequence of the changing climatic conditions and the emission scenarios being considered. We also wanted to see the difference in a 100-year and 200-year return period flood between the kind of historical and future generated values for near future under one and another scenario, and far future under one and another scenario. So these four are showing the difference for the 100-year flood. Again, if you look at the zoomed areas, you will be looking into the change or switch from this kind of bluish into yellow, orange, and red areas. Obviously, the change is significantly increasing with the distance in future, as well as the severity of the scenario, as kind of visible from the previous two slides. In the 200-year, you can see the last map showing almost bright red areas with an extremely high expected high change in the in the flood hazard in the future. And the last analysis was to actually look at the frequency or change in the frequency of the historical 100-year flooding for these four different analyses for the medium and severe emission scenarios, and for 200-year, the bottom two graphs for the medium and severe. The focus is on the areas blue and red. Red is showing the increase in the return period, and blue areas are showing the kind of decrease of the return period. It is a very, this scale is very hard to kind of see, but mostly populated areas are being subjected to this, decrease in the return period. So the severe floods may be hitting the mostly populated area of Canada more frequently under the changing future conditions. That kind of deriving conclusions from this part of the work, for the first time we utilized the Project 6 data, and I'm trying to kind of use that in understanding the changes in the floodplain regimes. We looked at the near and far future for 100 and 200-year flood event under two severe and less severe emission scenario. It is observed that the near and far future 100 and 200-year events will add to a rise in the flood hazards, or the basically inundation and inundation depth, as well as in the change in frequency, especially western, northern parts, and some other areas of the country. That brings me to the kind of end of my presentation, and I would like to kind of end up with some recommendations or the lessons learned. My objective and interest will be to use now this information that we have and create the National Flood Hazard Atlas for Canada, maybe make it in a kind of web-based form available for general public and organizations that may need this information. I think there is a justification to look at the areas that are being identified as the areas of the higher exposure in order to perform more detailed analysis on the finer scale. And because our work was focused on the riverine flooding, to include the coastal flooding into the analysis. I'm currently working on two additional projects. One is looking into downscaling. Now, this information, as I pointed out, our product is on a 1 by 1 kilometer basis. We are looking for now having appropriate methodology that we can bring this scale up to 20 by 20 meters. This work is being completed. And the second project is just at the beginning, where we are focusing on the compound flooding, trying to combine now the fluvial precipitation and storm surges, and basically derive the methodology that will be of more accuracy, of higher accuracy for the coastal areas that are not very well represented in the current work. For those of you who are interested, all these three different aspects are in the very recent set of publications. The first two looking into reanalysis and general methodology, and the second one dealing with the population exposure are already published and available. And the third one, I think it's available on the website in an unedited form. But we submitted the Galleprints, the proofs like 3 days ago. So I assume every day will be, this paper will be available also on the website of the journal. A lot of additional information and resources available on my website, or if there is an interest for other details, I will be very happy to respond. My email is available on the website. It's just a Simonovic, suwo.ca. With this, thank you very much for your attention. I know that this hour covered a lot of information, and I will be very happy to answer your questions.
Well, thank you very much, Dr. Simonovic. I definitely found it interesting, and I know I'm not the only one because we already have a bunch of questions lined up. I would just like to point out, if anyone has further questions as the discussion continues, just drop them into that Q&A icon at the bottom of your Zoom interface. And with that, I will get started with the first question. Something nice and simple. Do you use the NRCan EGS product for historical flood data?
NRCan or historic? You mean for the, I assume for the benchmark flood maps, yeah?
I assume so. They say historical flood data.
For the benchmark flood maps, we utilize the current maps being utilized by these different locations. And you remember the 6 different basins. We were in touch with the agencies, or we did review the government department websites which are providing this. So these 6 basins, we utilize the official maps. These maps, I forgot to mention that, so question is good. These maps are derived in different ways. Like a Red River map compared to Lower Fraser is derived, utilizing completely different methodology. But we decided to do the comparison because these are the kind of official maps being used in these basins.
Okay, thank you very much. And I'll move on to a related question, spinning off that one. Why did you choose to not include the National Hydro Network from NRCan instead of the OSM data or OpenStreetMap data that you used for your flood model?
It is a good question. I don't have a very very convincing answer. We did review all the kind of data that was required in order to kind of put this methodology together. And at the moment when we were kind of performing this review, I think the kind of OpenStreet data was already utilized by the CaMa-Flood modeling, and the CaMa-Flood modeling that we started with in this project was done good 4 or 5 years back. So we used the calibrated model, and that model utilized the data that was available at that time. So that was not changed, but with the kind of availability of the model or the availability of the data, that will be relatively straightforward task to replace or check or compare the maps obtained by utilizing different data sets.
Okay, thank you. Here's a question about the population exposed. It's a 2-parter. Is this using 100-year or 200-year flood maps, I assume? And how did you calculate the population exposed? For example, if only 10% of a census division intersected the floodplain, is that considered in how the population is calculated?
Okay, so answer to the second question first, yes. We assumed the uniform distribution of the population within the census area because we didn't have, or we didn't go to the different level of resolution in the population data. And the first question was that we did for both. We did analysis, and I did show results for both, for 100-year and 200-year return period. And we also did using the kind of flood data. All different floods, as well as, you know, high and very high flood exposure. So five different maps are produced that are available, and the data, the tables that I did show are simply the data extracted from these maps. I think, you know, kind of understanding the second question, there is definitely opportunity to kind of improve the resolution by going from the census division to lower scale, lower spatial scale. And with integration with our downscaling procedure, which is now being completed by my research group, I think we will be able to do that, you know, very easily. We will be having maps which are having resolution 20 by 20 meters. So then we can go to very small areas, maybe, you know, kind of boundaries of the urban areas, or even the sections of the different, you know, urban areas.
Perfect. And just because you just finished off on the downscaling, I would like to follow up with a question. Can we have more details about the downscaling method?
You mean, okay, I'm not sure. There are two downscaling methods I mentioned. One was already utilized in the process of developing these maps that I did show. The resolution of different reanalysis products was different, and the CaMa-Flood modeling was kind of performing the analysis or the calculation utilizing the resolution of the runoff information. And when the maps were, or the calculation completed, then we did the downscaling that to 1 by 1 kilometer, so that we have unique kind of grid across the country. The downscaling in that case was based on a distribution of the water volume, and obviously the difference and redistribution according to the kind of scale. The work that I am currently completing on the downscaling is much more sophisticated, and we are utilizing the kind of statistical method that combines some of the physical information, topography, volume, and so on, in the process of downscaling to very high resolution. As I pointed out, we are generating maps up to 20 by 20 meter resolution.
Okay, thank you. I'm going to combine two questions here because they're very similar. First one is, what is the purpose of using population data from sources other than StatsCan? And the second question is, why did you choose to use census divisions instead of dissemination area for exposure analysis?
The reason why we wanted to look at the other population data was looking a little bit outside of the Canadian borders. There are many places where this kind of global global flood modeling, floodplain mapping is being done, and kind of arriving to basic information of the population vulnerability requires combination with the population data, and in many places that's not available. Because we had very good kind of, you know, Stats Canada data, and we were in a situation that we can do this comparison and kind of verify or explain, you know, how these different data sets may perform. We thought will be of value to the research as well as the, you know, flood managers outside of Canada. that was the main reason for using not for the Canadian analysis. As you have seen, we mostly focused on utilizing the Stats Canada data. Why we use the census areas, the reason was simply the kind of computation requirement. The census, I mean, the finer resolution is possible, is easy to kind of implement through the same methodology. I didn't mention that we are talking here about millions of grid cells across the country and 293 divisions. The census divisions was kind of already pretty significant task. Most of the CaMa-Flood modeling was done utilizing the supercomputing facilities at our university through the SharkNet network, and required considerable resources in both time, space, number of processors, and so on.
Okay, thank you. I got a question here about how the way the flood extent changes with future climate. Do the boundaries actually change themselves, or is it just the water depth? The person who posted this question said it's a little hard to tell in the image. They're not sure if it's pixel depth or total extent that's changing over time.
Okay, both are changing, and maybe I went very fast through the presentation. I hope it will be made available by ICLR to people who are interested. We did, and I did show both types of maps, change in the water depth, which I consider to be or we call it as a flood hazard, as well as the inundation extent. The CaMa-Flood model is producing these two pieces of information, and so we were able to kind of do that analysis on the extension, or the inundation level, and we were able to kind of show both. For the future, the both scenarios, both periods, the closer and the further, and both scenarios, medium and extreme, are showing increase in water depth as well as the increase in inundation. Pretty significant for the extreme SSP5 emission scenario.
Okay, thank you. And for the record, the recording of this session will be made available on the ICLR website, and I believe we have a YouTube channel as well in which it'll go up on. Moving from the technical stuff to more to community resiliency implications, one of the questions asked was how much of the increase in exposure due to climate change, or how much of the increase in exposure is due to climate change versus zoning and building in more high-risk areas?
That was not, I mean, answering this question will be kind of impossible using this type of analysis. We can show the change, but understanding why is the exposure increasing? Is this due to the kind of more people coming closer to the river, or is it due to the river spreading or floods spreading to larger area? Will require also more detailed kind of information on the dynamics of the changing exposure. So like how many new development or the population entered into particular area in particular time interval. That information we do not have. Predictions of the change of the location of the population or the population dynamics for the 100 years from now, I don't think is available. All the population prediction data is focusing on the total number, and the total numbers are subject to, again, various scenarios being used in deriving them.
Okay, thank you. And it looks like we have two very similar questions here about Northern Canada. The first being, what kind of conclusions can you make about flood impacts in Northern Canada? And the second is, do you have data and analysis for the Northwest Territories and Yukon?
Yes, we do have second question, answering second question. Yes, we do have the data for the whole Canada. So including the northern territories. So this analysis is done for the whole country, and the whole country being divided into grid cells, and for each grid cell you have the information. Therefore, you can see the exposure as well as the kind of flooding or floodplain extent in these regions. The change under the kind of climate scenarios in the third analysis, I think I did show and pointed out that there is a change from the higher most of the northern Canada is moving into higher level of flood hazard. This is the kind of consequence, obviously, of the changing climate conditions, which are being represented through the change in runoff that is utilized from the climate models used, the 17 climate models used for prediction of the future floodplains or floodplain or future mapping of the future floodplains.
Okay, thank you. And we have a few questions left here, all about floodplain zoning and mapping. So to start with the first question, I understand that you have found that about 10% of Canadians live in zones with high risk of flooding. Does data exist to determine when these developments took place? In particular, were these vulnerable properties established before flood risk was known and mapped, or have these developments taken place in the last 50 to 60 years or so?
We do have the information only, as I did show, or the Stats Canada provides the information from 2006 to 2019. That's all what we were able to kind of obtain, and that's how we did show the change in the exposure. Again, the maps that are produced through this work and the exposure that is being like 4 million people being in the 200 year and so on are based on the just the total population numbers. We do not have, or the Stats Canada is not providing the data in the form that we can find out, for example, when was the development introduced to a particular census area or not. We have the total number for 2010 and then 2011. So I think you can kind of infer that there is a change in that number. That's the consequence of people kind of moving closer to the river or moving into the floodplains. However, in the same time, you have a change in the floodplains, and therefore, I think answering directly this question, you will need probably to focus on the particular area, look at the kind of dynamics of the population change, and also in the same time, look at the dynamics of the change of the floodplain or inundation boundaries. And that will be, I think, then possible. Then it will be possible to answer answer that question. This was not done, in kind of our analysis, because we were looking the kind of whole area and we were looking into total kind of exposure. But I think this is a pretty important question, and it can be relatively easily performed with the methodology that is now available.
Okay, thank you. And I'm going to combine our last two questions together because they're very similar and they're a very good way to finish off the entire conversation. So the first one is, I understand that locations in Canada are designated either in the floodplain or out, and that if you're inside the floodplain, development is prohibited, and if you're outside the floodplain, development is allowed. Should there be a third category of locations that are outside the current floodplain, but expected to be in the floodplain of the future due to climate change? And the second question, and a bit more general one, will there be efforts to update floodplain zoning based on the results of these models?
Yeah, these are both questions are extremely important and pretty significant questions. I can provide the kind of my view. I feel that the climate change is, and not only climate change, also the population, land use, and so on. So I call that global changing conditions are changing the exposure as well as the hazard. So the logical response to that statement will be, yes, we need to update or change the criteria more often. The number of conservation authorities in Ontario, as far as I know, were looking into kind of these questions and looking into ways how to bring the climate change into flood zoning, and should the criteria be changed, should the same criteria be used, but with the future kind of flow conditions predicted by different modeling tools. We are, I think, facing very significant, potentially very significant impacts, very costly. The damage is definitely increasing, and the increase in the damage can be a consequence of both changing the hazard as well as this exposure. So kind of focusing on this question, on either zoning or change of zoning, or incorporating the climate change into the current zoning, I think it's justified, at every location in Canada.
All right, and that wraps up all of our questions. I would like to provide a big thanks to Dr. Simonovic for taking time out of his busy schedule to provide us with that informative and interesting presentation. And I'd also like to thank you in the audience for joining us today and providing us insightful questions. If you are interested in the recording of this session, it will be available on our website and YouTube channel shortly. And once more, before we go, I'd like to take the opportunity to advertise next month's Friday Forum, which will be on the topic of Edmonton's approach to flood management and be presented by Susan Ansell, the Director of One Water Planning for EPCOR Services. Thank you all for attending, and have a good day.